Today I made the video on the mechanism of organic reactions. Introduction. During the study of organic chemistry, we come across numerous reactions which the organic compounds undergo. As we study these reactions, we not only want to know which reactant give rise to which product, but we also interested in knowing how it happens. Do the reactants change directly into products in a single step, or does not reaction take place by the several steps through the formation of reactive intermediates? The complete description of how a particular reaction takes place is called the mechanism of the reaction. It tells us which bonds are broken and in what order, and what bonds are formed and in what order. It also tells us what kinds of intermediates are involved and what are the relative rates of different steps. We shall now consider some important notations and basic concepts involved in the study of the organic reaction and their mechanisms. Next one is important notation. Reaction of unique compounds involve the breaking and making of the covalent bonds and the movements of electrons from one side to another. To indicate these changes, certain notation involving in the use of different kinds of arrow have been adopted as discussed below. First one is curved arrow notation. It is very useful notation in which a curved arrow indicates the movement of electron as bond in reactant are broken and new bonds in product are formed. It means that an electron pair moves from the atom at the tail of the arrow to the atom at the head of the arrow. It is illustrated below the help of a reaction between the water and the hydrogen chloride. The electron pair moves from O2 of H2O to H of HCl. The bond between H and Cl breaks and electron pair moves to Cl. After reaction, the electron pair that moves from O from a new bond with H to give S3O positive ion. The electron pair of HCl bond goes to Cl to form Cl negative. Similarly, reaction between the acetylene and amide ion NH2 negative to form acetylene and ion CH triple bond C negative, and ammonia may be also as follows. Next one is a half-headed arrow. As will be discussed in the section 2.3, sometimes a bond between atoms break in a manner that each atom gets electron of the shared pair. To prevent this type of symmetrical bond breaking and bond making, half-headed arrow are used in shown ahead. It may be noted that a half-headed arrow is used for showing the movement of an electron, while a full-headed arrow is used for a pair of electrons. Next one is double-headed arrow. This type of arrow are placed in between the various canonical structure of a substance which exhibits resonance. This is to indicate that the actual structure is a hybrid of these structures when are hypothetical or not real. For example, double-headed arrow are placed between the two major canonical structure of benzene to indicate that the actual structure of the benzene lies in between two structures which do not have any real existence. Type of bond cleavage. Reaction of organic compounds almost invariably take place through the breaking and the mention of a covalent bond. Depending upon the nature of the given organic compounds, the nature of the attacking reagent and the reaction condition, a bond between the two atoms of a molecule may be cleaved or broken in different ways, producing different types of reaction intermediate. The different possibilities are illustrated below by considering a covalent bond between the two atoms A and B. First is homolytic cleavage or homolytic fission or homolysis. This involves the breaking of a covalent bond in such a way that each atom separates with the electron of the shared pair. This leads to the formation of highly reactive neutral particles containing odd or unpaired electrons are shown as free radicals. It may be seen that the homolytic cleavage of a bond is shown by the using half-headed arrow in pairs. Second is hydrolytic cleavage or heterolytic fission or homolysis. This involves the breaking of a bond in such a way that the Both the pairs of electrons are shared or carried away by one of the atom. The first one is if A is more electronegative than B, and second is if B is more electron than A. Second is homolytic fission leads to the formation of a charged ionic species, one having a positive charge and other a negative charge. If both the shared electrons are taken away by A, it should convert it into an anion or B into cation. On the other hand, if both the shared electrons are related by the B, it would change into an ion while a would from a cation are shown above. Quite often, the ionic species formed by hydrolytic fission bear the positive or negative charge ion on carbon. Such ionic species are known as carbocation, earlier called carboanion and carboanions, according as carbon carries positive or negative charge. It may be mentioned that the particle covalent bond are undergo under either homolytic cleavage or heterolytic cleavage. Under different conditions, the bond dissociation energy or homolytic cleavage is considerably different from that of a heterolytic cleavage. In general, the values of the homolytic are while quite high of heterolysis. For example, the bond dissociation energy of a Cl bond in the CH3Cl are homolytic and heterolytic ways are 351 and 949 kilojoule per mole respectively. Homolytic fission is H3Cl in after reaction H3C free radical plus Cl free radical. Heterolytic fission in H3C bond Cl after reaction HC H3C free radical plus HCl negative electrons. Like reaction intermediate, the student is already familiar with the fact of organic reaction. The starting substances seldom changes into the products directly in one step. On the other hand, the reactants first change into intermediate substances called reaction intermediate, which ultimately yield the products. The reaction intermediate are generally very unstable and reactive substances which cannot be even isolated. We will now briefly deal with the main reaction intermediate which we often come across in the organic chemistry. Carbocations, earlier called carboanions. What are carbocation? Carbocation is a cation in which the positive charge is carried by a carbon which has only 6 electrons in its valence shell. For example, CH3 and CH2 free radical are simple carbocation known as the methyl cation and the ethyl cation respectively. A carbocation may be assumed to be a fragment of a molecule from which an atom or a group is singly bounded to a carbon gets moved along with the pair of bonding electrons. For example, if the bromide ion is removed from a stable molecule of methyl bromide, tributyl cation would be performed as shown below. Carbocations are very short-lived and highly reactive species. The reactivity of carbocation is due to their tendency to complete the octet of electron-deficient carbons. As a result, carbocations undergo a variety of reactions. Formation of carbocations. Carbocations are generated in many different ways. Some of the reactions in which they are formed are given below. First one is direct ionization. The carbon halogen bond CX in many organic halides generates carbon cation in the presence of a highly polar medium. Some example you have seen on the screen. This method is of a particular importance in the formation of relatively more stable carbocation. Second is by the pronation of unsaturated carbons. Unsaturated carbons such as carbonyl compounds and nitriles means carbocation are treatment with proton donating for examples. Third one is from compounds containing an atom with a lone pair of electrons and organic compounds having a lone pair of electrons on an atom, especially oxygen, is treated with an acid. Protonation of atoms takes place. This is followed by the elimination of a simple molecule containing this atom is furnished a carbocation. For examples, have you seen alcohol converted into carbocation and the ether converted into the carbocation? Fourth one is by the decomposition of diazonium salt. For example, primary amines after reaction make the diazonium cation. After reaction, they form the carbocation. By the action of superacid and alkyl fluoride, for example, you have to say RF plus SbF3 after reaction intermediate is FSO3H and after reaction R positive plus SbF6 negative. Note the term superacid is used in the experimentally strong acidic solution SbF3 as the structure and carbocation. Unhybrid orbitals such as in the same and involved in the formation of the three bonds which is often atoms. The unsaturated hybrid p orbital remains vacant. Thus the carbocation has a flat structure as represented in the right hand side. The bond angle around the positive charge cation is nearly 120 degrees each. Classification of the carbocation and their order of stability. Carbocation are classified as primary, secondary, and tertiary according as the carbon bearing the positive charge is primary, secondary, or tertiary in the nature. In addition, in the methyl ion having one carbon is generated as a special case. First one is methyl cation, second one is ethyl cation primary, and the isopropyl cation is secondary, and the tetrabutyl cation is the tertiary. It has been established that the order of the stability of a carbocation is first one is tertiary, is highest order of stability, then is secondary, and then is primary, and then is methyl. Explanation of the relative stabilities of the alkyl carbocation. A basic principle involved in discussing the relative stabilities of carbocation is that how does a given factor influence the magnitude of the positive charge carried by the electron deficient carbon of the carbocation is a period and factor which tends to disappear the positive charge by distributing it over the rest of the molecule stabilize the reaction. In contrast, many factor which tends to intensify the positive charge disabilities the carbocation. The relative stabilities of the alkyl carbocation are given above can be explained in terms of inductive effect and the hyperconjugation in terms of the above principles. Inductive factor, this is the main factor operating in the determining the relative stabilities of carbocation. As it well known, the alkyl groups are more electron releasing than hydrogen. As such, a alkyl group attached to positive charge carbon of a carbocation tends to release electron towards that the carbon due to its positive I defect in the positive charge of the carbon gets dissipated. This dispersal of charge stability of the carbocation. Now the more of a number of the alkyl groups greater the dispersal of the positive charge and therefore for more the stabilities of the carbocation. This is why the tertiary carbocation having three alkyl groups attached to the positive charge is more than secondary carbocation with the two alkyl groups. The secondary ion in term of more than a primary carbocation such only one alkyl group. The methyl carbocation has does not alkyl groups and therefore such list first second carbocation primary carbocation. The methyl carbocation list disciple of positive charge list stability. And the tertiary carbocation has the maximum dispersal of positive charge and the maximum stability. It is quite evident that the presence of the electron during subsequent negative effect of with the disabilities the carbocation are intensifying the positive charge on carbon. Second one is hyperconjugation. The concept of hyperconjugation is also the some extent responsible for the observed order of relative stabilities of carbocations. Hyperconjugation can take place here through the overlap of sigma orbital of the alpha CH bond of alkyl group and the empty p orbital of carbocation. Taking CH and C free radical to represent a carbocation in general dislocation of electron through sigma and pi orbital overlap may be shown as due to this overlap the delocalized electron and bind together three atoms. Two carbons are hydrogen to the some extent. In terms of resonance, the above situation may be dissipated as. The net result is that in the actual structure, CH bond is slightly lesser than a single bond. The carbon-carbon bond has some double character, while the positive charge is partially across moderated by hydrogen atom. This partial accommodation of positive charge over hydrogen leads to the dispersal of charge and consequently disabilities the ion. In methyl carbocation, no such dispersal of charge is possible because hyperconjugation does not take place. In ethyl carbocation, primary with contains 3 alpha hydrogen, the positive charge can be disappeared over 3 hyperconjugation structures possible in addition to the normal structure as shown below. In isopropyl carbocation secondary which contains 6 alpha hydrogen, there will be 6 hyperconjugation structure possible. In tributyl carbocation tertiary which contains 9 alpha hydrogen, there will be 9 hyperconjugation structures possible. B structures as the number of contributing structure and with the dispersal of a charge becoming more, the stability of the carbocation goes to the increasing. Thus, the relative stability of the alkyl carbocation has may be due to the combination of the inductive factor and hyperconjugation, although it is usually explained in terms of inductive factor and the conjugation of positive charge with double bond cleavage resonance stabilizes the carbocation in which the positive charge carbon is conjugated with the double bond or a benzene and the electron of a double bond. The instance alkyl carbocation is a resonance hybrid of the two equivalent structures as shown below. It is apparent that the positive charge of the carbon of the carbocation gets disappeared over the carbon atoms as the alkyl cation acquires greater stability and it is found to be more stable than the simple alkyl cation. Similarly, benzene carbocation is greatly stabilized by the resonance as shown below. It is evident that the carbocations having the more than one phenyl group attached to the positive charged carbon atom would be still more stable. This is because there will be a greater dispersal of positive charge due to the larger number of contributing structures. Accordingly, diphenyl methyl carbocation should be more stable than the benzyl carbocation. 3 more contributing structures. Similarly, triphenyl carbocation would be still more stable. In fact, triphenyl methyl it is so stable that some of the salt which is fine chloride may be isolated, stored and months. Effect of strain on the stability of the benzyl carbocation. It can be readily understood that the presence of electron releasing group at the ortho and para position of the phenyl group with respect to the position where CS2 positive group is attached will tend further stabilize the benzyl carbocation. On the other hand, the presence of the electron withdrawing groups as this position would have the position effect. For example, the order of stability of the following substrate benzyl ions. S ratio has a plus I effect and O2 N has a minus I effect. Fourth is the instability of a vinyl and phenyl carbocation. The carbocation in which the positive charge is carried by double bonded carbon atoms such as vinyl carbocation CH2 double bond CH positive and phenyl cation C6H5 positive are found to be highly unstable. This is because these ions do not undergo resonance stabilization at all. The reason for lack of resonance is that of the vacant orbit of the cation carried the positive charge is perpendicular to the double bond and therefore it cannot participate in resonance. Determination of the relative stabilities of the different kinds of carbocation. It is evident from the above discussion that the stability of carbocation is primarily related to the dispersion of the charge carried by a positive charge carbon. The dispersal of charge may be due to the inductive effect and the hyperconjugation effect of the resonance effect as explained above. The relative stabilities of the different kinds of carbocation can be measured by hydroelectric bond dissociation energy leading to the formation of the carbocation. On the basis of these values of the decreasing order of stability of some of the common carbocation are given ahead. First one is tetrabutyl is more stable than benzyl and is more stable than isopropyl. It is more stable than allyl. It is stable than the N-propyl and is then ethyl and then next is vinyl and then phenyl and then is methyl. It may note that however the benzyl propyl allyl carbocation are most equal stable. Similarly, vinyl phenyl methyl carbocation have nearly the same stability. Arrangement of carbocation 1 to shift. An important feature of it is that they are undergo arrangement reaction to form stable carbocation. This arrangement involve the shift of either is hydrogen alkyl groups along with the direction pair from an adjacent carbon to the positive charged carbon. Such shifts are known as 1 to shift. The shift of a hydrogen is known as 1 to hydride shift, while the latter group is as 1 to alkyl shift. The carbocation thus formed contains a new charge center and is more stable than the original carbocation. For example, 1 to dihydride shift, next 1 to methyl shift. The arrangement of carbocation discussed during the letter of Say's book. Carbocation. The carbanion is an anion which the positive charge is carried in by a carbon. The carbon has 4 bonds, and one and more than atoms possess a lone pair of electrons. For example, C negative. The triple bond OH is a simple carbanion known as acetylene ion. A carbanion may be assumed to be fragment molecular then one of the atom are gaseous singly bound to a carbon is removed without a bonding pair of electrons. For instance, removal of a hydrogen of a methyl part of a acetylene molecule is as a hydrogen ion result in the formation of a carbanion as shown below. Acetaldehyde is after reaction then it form carbanion. Carbanion is highly unstable and one of the most reactive reaction intermediate in organic chemistry. They are very frequently involved in the reaction of aldehyde, ketone, ester, etc. Their relatively is due to the fact of negative charge carbon in them has got a lone pair of electrons. It is a strong tendency to donate this lone pair of some electron deficient species. Therefore, carbon may easily participate in many reactions. Formulation of carbanion. There are two main methods by which carbanion are generated are given below. By the dissociation of a molecule in which an atom or group singly attached to the carbon leaves it without the electron pair. This is in most the cases, the leaving group is a proton, hence a pair of required is calculated to the process. Thus, the formation of carbanion is an acid-base reaction. Since the presence of the carbon electron attacking substrate as a carbonyl cyano or nitro group on the carbonyl has hydrogen makes the hydrogen reactive more acidic than therefore more easily removable a proton, and generation of the carbocation from compounds play a very important role in chemistry. To remove a proton from a hydrocarbon, very weak acid, very strong base such as regulation in liquid ammonia has to be used. But the aromatic compounds of the type triphenyl methyl generated carbocation very easily in the presence of a base. Triphenyl methyl after reaction then it forms phenyl methyl anion. It may be pointed out from apart from protons, other living groups and also known as to be by the formation of carbocation. For examples, then by the addition of a nucleophile or a carbon multiple bond. But this type of condition occurs only when the double bond is activated towards the nucleophile to attack the electron withdrawing groups such as carbonyl, cyano and nitro groups. For examples, then is structure of carbon and the negatively charged carbon or carbocation is state of hybridization, so that the hybrids orbitals are directed to the vacant of the carbon corners of the tetrahedron. Three of the hybrid orbitals are involved in the formation of single bond with the other atoms, while the fourth orbital contains a lower pair of electrons. Thus, carbanion having distorted tetrahedron or pyramidal structure as shown as the right hand. But the bond angle between the negative charge carbon and less than the 109 degree 28 minutes. This is because lone pair repulsion is greater than the bond pair repulsion. It may be pointed out, however, in case of carbanion is which negative charge the carbon having the lone pair of electron is in conjugation with a simple bond. The carbon has a planar structure. Some example of carbanion having a planar as given below: allyl carbanion, benzyl carbanion, and the acetylide carbanion. Classification of the carbanion are in their order of stability. Like carbocations, carbanion are also classified as primary, secondary, and tertiary carbocations according to the negative charges carried in primary, secondary, and tertiary carbocations. Methyl carbanion is considered as a special case. And you see in methyl carbonane, ethyl carbonane primary, isopropyl carbonane is secondary, butyl carbonane is tertiary. In order of stability, the different classes of carbonane has found to be best is methyl, then is primary, secondary, and then explanation of relative stabilities of carbon ion. First one is inductive fact. The above the order of stability is primary, secondary, and tertiary carbon ion just justified on the basis of electron releasing plus I effect of the alkyl group. Due to this, alkyl group tends to increase the electron pair towards the electron deficient species. Now, the greater the number of alkyl group in the carbon ion, then more would be its reactivity, and the lesser its stability. This is keeping under the stability of it is when in the presence of the electron withdrawing substituent minus I effect and such as NO2 negative to C triple bond and will be stabilize the carbon and by dissipating the negative charge on carbon. For example, para-nitrophenyl carbon is more stable than the due to the presence of the electron withdrawing NO2 group. On the other hand, presence of having psi effects such as R, OH will be destabilize the carbon and by intensify the negative charge. Second is hybridization. The relative stability of some carbocation also be compared in terms of hybridization. For example, let us consider the following carbanion. Alkyl carbanion is sp, kynyl carbanion is sp2, alkyl carbanion is sp3. Note that it is may be noted that hybrid orbit having the grating as character and relatively more attacking tendency to have the lesser as character as that the greater electronegative chemistry is more accumulated negative charge is much more special. Therefore, negative charge carbon of the alkyl group accumulated negative charge more than alkyl. Therefore, the alkyl element is in terms of resonance and conjugation. In case of carbon even the carbocation which stabilizes the conjugation exact stability to the dissipating negative charge on the shown alkyl carbon ion. Similarly, benzyl carbon ion is highly stabilized by the resonance as shown below. It is evident the more the number of the phenyl groups attached to the carbon carrying the negative charge, greater will be the dispersal of negative charge due to the large number of contributing structures. This is why diphenyl methyl carbon ion is more stable than the benzyl carbon ion. For the same reason, triphenyl methyl carbon ion is one of the most stable carbocation. Carboanion. The carbanion obtained by the removal of alpha hydrogen from the carbonyl compounds are shown stabilized by resonance as shown. Free radicals. What are free radicals? A free radical is an atom or a group having an odd and unpaired electron. It is dotted by the dot against the symbol of the atom or a group of atoms. For example, Cl free radical stands for a distance free radicals, while S3C free radical do not say methyl free radical. Radical are electronically neutral species which are usually formed by the homolytic cleavage in this reaction taking place gas phase or in polar solvent. For example, ClCl after reaction to Cl free radicals, chlorine free radicals. Due to the presence of the odd electrons, free radicals are paramagnetic in nature. For free radicals are highly short-lived species. They are extremely reactive as shown as they are formed. They intimately participate in some further reaction. Their greater reactivity is due to the tendency of odd electron in them to be paired up. Formation of free radicals. There are two main methods of free radicals are usually found by thermal or photochemical photolysis of a covalent bond. For example, CS3 4 times Pb tetramethyl lead heat, then it form lead plus 4CS3 radical methyl free radicals. Benzyl peroxide then gives heat, then it forms benzyl oxide free radicals. After that it forms phenyl free radicals plus CO2 gas. Diacetyl in which sunlight we form acetyl free radical. By oxidation reduction reaction allowing gain or a loss of a single electron. For example, RC double bond O and single bond O negative. After reaction RC double bond O or and a single bond O free radical. After reaction then it form R free radical plus CO2. Structure of free radicals. It may be pointed at in case of free radicals containing carbon The state of hybridization of a carbon atom having one odd pair is clearly established. However, there is strong evidence to evident that the most of the alkyl free radicals, such as methyl radicals, are actually planar. This means that the carbon atoms carrying the odd electron in sp2 hybridized state, the three coplanar hybrid orbit are involved in the formation of the three single bonds with other atoms. The unhybrid p orbital, which lies in a plane of right angle of the plane of the hybrid orbital, carries the odd electron. The bond angle around the carbon carrying the odd electron is approximately 120 degrees each. Classification of free radicals and their order of stability. Alkyl free radicals are classified as primary, secondary, and tertiary according to the odd electron carried by its primary, secondary, and tertiary carbon atom. But methyl radical S3 is carrying the one carbon is treated as a special case. The order of the stability of different types of free radicals relative to the alkynes with they are derived as found as first is tertiary, secondary, then primary, then methyl. This order is derived from a bond dissociation energy involved in their formation. The lesser the bond dissociation energy in the formation of free radicals is more stable. To illustrate the above statement, let us consider the homolytic fusion of an alkyne into a alkyl radical and a hydrogen atom, that is RH after reaction in R free radical plus H free radical. It is apparent that the H del H of such a dissociation process must be equal to the bond dissociation energy of the bond between the concerned hydrogen and the carbon of the alkyl group. A study of the del H of the several reactions involving the dissociation of different alkanes to form the different classes of alkyl radicals showed that the amounts of energy required to form various classes of alkyl radicals are in order: methyl, then first is methyl, then second primary, then secondary, then tertiary. Most energy to required from free one radical, then the order it means the relative to the alkane from which it is formed, and the radicals contains more energy than the other than it is hence less stable. This is may be concluded that the relative to the parent alkane in case of order of stability of free radicals is then first is tertiary, secondary, then primary, then methyl. It must be emphasized that this order is based only on the differences in energy between the alkyl radicals and the present parent alkane is. In such cases, it does not reflect the order of the soluble absolute stability in the individual radicals. To make the point clear, let us consider the case of methyl alkyl primary radicals. The difference in energy between the methyl and methyl radicals are del H for the reaction CS3C. After reaction, CS3 free radical plus H free radical being 433 kilojoule. It is more than the difference between the ethane and methyl radicals. H del H of the reaction is CS3CH2. H after reaction CS3CH2 free radical plus H positive free radicals being the 410 kilojoule. There merely means that stability of the methyl radicals relative to the methane is less than the stability of ethyl radical relative to the ethane. Explanation of the relative stabilities of alkyl free radicals. What is hyperconjugation? The relative stabilities of alkyl free radicals are explained primarily in terms of concept of hyperconjugation, with the concept exception of methyl free radicals. All other alkyl free radicals undergo hyperconjugation through overlap between a sigma orbital of the alkyl group and a p orbital containing the odd electron, taking to represent alkyl free radicals in general. Decollocation through a sigma and pi orbitals may be in adjacent finger. As a result of the overlapping and delocalized electrons having in binding together, they form atoms and one hydrogen to the same extent. In terms of resonance, the above situation may be represented in the saying that the given alkyl free radicals in resonance hybrid of the two contributing structure as shown. This means that the CH is slightly less than the single bond C single bond C has some double bond character, as the odd electron is partially present in the hydrogen atom. The actual number of the contributing structure of the extent of the relocation of the odd electron depends upon the nature of the alkyl radicals. Is more number of the contributing structure on the more extensive relocation, the more stable is the radical. Let us instance compare the relative Solubilities of methyl, ethyl, and ethyl radicals in the methyl radical conjugation is not possible, and the non-delocation of odd electron take place, but in methyl radicals primary there is considerable delocation of odd electron due to the contribution of from neutral structure, and the three away conjugation are shown. As a result of stabilization due to the resonance of delocation, ethyl radical is about 15 kJ per mole more stable than the methyl radical. As they pass the isopropyl radical second, it may be 6 hyperconjugation structures in addition to the normal structures. Due to the greater relocation result from more contributing structures, isopropyl free radical is more stable than the methyl free radicals to extend to the 37.6 kJ per mole. Similarly, tat butyl radical tertiary is stabilized by to the extent of 50 kJ per mole, since it is has 9 hyperconjugation structure in addition to the usual structure, and therefore are very extensive delocation of electron take place. In general, in order of stabilities of alkyl primary is tertiary, secondary, primary, then is CS3 free radicals. Resonance and the conjugation, resonance or conjugation, like carbocation and carbon and free radicals exhibit more resonance or conjugation as more stable than the simple alkyl radicals. For example, alkyl free radicals is more stable than the alkyl free radicals because the former is stabilized by the resonance. Similarly, benzyl free radicals is highly stabilized by the resonance. It can be readily understood that triphenyl methyl free radicals is very highly stabilized is by resonance due to the presence of the three phenyl groups attached to the carbon carrying the odd electrons. Determination of the stability of the some common free radicals or different kinds. The relative stability of free radicals can be measured by the determining homolytic bond dissociation energy of RH bond. The relative stability of some common free radicals are given below in decreasing order. CH2 double bond CH, then is single bond CH2 free radical. Then is carbenes. What are carbenes? Carbenes are neutral divalent chemical species in which carbon is covalent bonded to the atoms and has got two non-bonding orbitals having two electrons between them. In other words, carbenes in carbon 9 a neutral carbon atom having 6 electrons in the valence shell, out of which 2 are unshared. The most common carbenes are CH2 free methylene and CCl2 dichloromethylene. Carbenes are highly reactive species having a very short period life. Disocarbenes, an interesting feature of carbene structure as in they may exist in two distinct states, but in singlet carbenes there are carbenes in such unshared electrons are paired. They are present in the different orbitals. Second is triplet carbenes. These are carbenes in which unshared electrons are not paired. They are present in different orbitals. For example, the methylene carbenes have either of the same two structure depending upon the formation. Singlet methylene unshared electron paired, and the triplet methylene unshared electrons are not paired. Different carbenes present the bi-radicals, divalent free radicals. Formation of carbene. There are the two methods generally employed by the generation of the carbenes by the thermal or photochemical decomposition of aliphatic diazonium compounds, ketones, or cyclopropanes or oxygens. For example, dimethane, diazomethane. After reaction, the methylene carbenes then form by the action of the base of stable halogen compounds. This method is usually employed for the generation of halogen carbenes, and the base commonly used in the potassium tioxide. Then it may be noted that their variation H positive and Cl negative are removed from the same carbons. Alpha emission takes place as a well. Example of reaction in which carbenes is formed as intermediate is remote reaction. If phenyl is given as salicylaldehyde, it involves the formation of the dichlorocarbenes. CCl2 is an intermediate. Structure of carbenes in singlet carbenes. The carbene is in a state of sp2 hybridization of these sp2 hybrids orbitals to or used forming two singlet carbon with a monovalent atom or group attached to the carbon. The third sp2 orbital consists of the unshared pair of electrons, while the unhybrid p orbital is empty. The formation of in triplet carbon, the central carbon is in the state of hyperconjugation. The 2sp2 hybrid is used in forming singlet bonds with the two monovalent atoms or group attached to the carbon. The two unhybrid sp orbital containing one shared electron each. Relative stability of carbons, and in this explanation it may be found that the triplet carbons are lower in the energy and therefore more stable than the singlet carbon. This is because the placement of the two electrons in a single orbital is singlet methylene involves the electron repulsion energy which must be overcome to pair of two electrons in terms of orbitals. On the other hand, in triplet carbons, the two electrons occupy different orbitals in the same repulsion instance as less. These single methylene have greater energy and than a triplet methylene. Then the difference is about 37.6 to 46 kilojoule per mole. Comparison of single and triplet carbons. In single carbon, is the in this two unshared electrons are present at the pair of orbital. In triplet carbons, it in this of two unshared electrons are present at the two unpaired electrons in different orbitals and represented by radical. In single carbon, it is relatively less stable. Triplet carbon is relatively more stable. The central atom is sp2 hybridized in singlet carbons. Triplet carbon and singlet carbon is sp. Nature of reagent. The two substances react together. One of the substances regarded as the taking reagent while the other is taken as substrate. Substances which get attached to the new substance formed as a result of reaction are called products. Thus, the occurrence of a chemical reaction may be dissipated as substratum plus attacking reagent, then it forms product. It may be pointed that a term attacking reagent is usually employed by the substances or whose presence brings around a chemical change in the given substance's substratum to form a product, but the use of the two terms in a purely relative. A particular substance may be termed as a product in one reaction and attacking reagent in others. However, the following conventions are generally followed in the use of two terms. First is in the reaction between the inorganic and the inorganic substance. The organic substance is treated as the substratum while the inorganic substance is taken as the attacking reagent. For example, iodoethane is substratum and the plus attacking reagent is KOH aqueous solution. Then it forms C2H5OH plus Ki. Second is in a reaction between the two organic substances. The substance which supplies the carbon atom in the formation of a new bond between the carbon atom and the hetero atom is treated as substratum. The other substance is taken as the attacking reagent. For example, ethanic acid is substratum, ethanol is attacking reagent after a new bond formed. In a third is in a reaction between the two organic substances involved in the formation of carbon-carbon bond of the substance is attributively assumed to be the substratum while the other is taken as the attacking reagent. Example, benzene is substratum when the ethanol chloride is attacking reagent, then it forms the new structure. Classification of reactant reagents. There are three types of attacking reagent taking part in the organic reaction. There are free radicals. Their formation and the reactive has already been discussed. Second is electrophilic reagent. Electrophilic reagents. An electrophile electron knowing participate in a reagent containing an atom which is deficient in electron because of the presence of electron deficient atoms such as then tries to seek electron from other sources and thus behave as Lewis acid and it attacks a molecule at the point of high electron density. Types of electrophile. There are two types of electrophile: positive charge ions or positive electrophiles. Positive charge ion is a hydrogen ion and hydronium ion, and the chloride ion and nitronium ion, and the carbon has electrophilic reagents. Second is the neutral electrophiles. These are the electrophile reagent in which the electron deficient atom does not carry any charge. For example, AlCl3, FeCl3 and BF3 belong to this category. There are certain substances in which the central atom has complete octet of electron and the still it is tendency to coordinate more electrons due to the presence of empty d orbital SnCl5. Afford an example such as electrophile. Carbons also act as electrophile because the carbon in them are only 6 electrons rather than an octane. Reactions involving electrophile agents are known as electrophile reactions. Third one is a nucleophile reagent. A nucleophile reagent or a nucleophile, a nucleus serving group. Is a reagent containing an atom having an unshared or non-pair of valence electron. Because of the free of the electron, such a reagent in search of a site that which of the share electrons in which behave as a base. Lewis concept of base is that a molecule a point of low electron density. For example, consider OH negative and the oxygen present in ion contains unshared pair of the electrons. Due to this reason, OH negative ion attacks any molecule containing a center of the low electron density and is sure in the that point. Type of nucleophile are two types: negative nucleophile or negatively charged. All negatively charged are such as hydroxyl ion, halide ions, alkylide ion, cyanide ion. The carbon ion as nucleophiles. Neutral nucleophiles are nucleophilic reagents such as contain ion lone pair of electrons but do not carry any charge. Water, H2O, ammonium, alcohols and are neutral nucleophiles. Reaction involving nuclear reagent are nucleophilic reactions. Classification of organic reactions. The reactions may be broadly classified into the following categories. These are substitution or dispersion reactions. Second is addition reaction, elimination reaction, rearrangement reactions, isomerization reaction, condensation reaction, molecular reactions. Substitution reactions. A substitution reaction is that involves the direct displacement of hydrogen atom or some other group of molecules by some other atom or group without any change in the structure of remaining part of the molecule. The product obtained in known as substitution product and new bond, new atom or groups which enters the molecule is such a substituent. For example, the with chlorine react with methane in presence of diffused sunlight. The hydrogen atoms are replaced by the chlorine atoms or other than leading to the formation of substitution products. CH4 plus Cl2 after reaction then form methyl chloride plus HCl. Similarly, the reaction of the methyl iodide with the aqueous solution of potassium hydroxide to form methyl alcohol is substitution reaction. Methyl iodide plus aqueous KOH, then it forms the methyl alcohol plus Ki. Substitution reaction may be involve free radicals, electrophilic or nucleophilic reaction according to their subdivided as free radical substitution reaction. For example, halogen of alkyne is a free radical substitution reactions. Act of nitration and sulfonation of benzene are important example of electrophilic substitution reaction. Nucleophilic substitution reaction of alkyl are nucleophilic substitution reactions. Addition reaction. An addition reaction involves the combination of between the molecule of a two reacting substances to form a single compound known as the addition product. One of the reactant is such a reaction always contain notable bond in a molecule. For example, ethylene after plus Br2 after converting in ethylene dibromide. Addition reaction may be also involve free radicals, electrophilic or nucleophilic reactions such in subdivided as free radical substitution addition reaction. Addition of HBr to alkenes is the presence of benzyl peroxide as well as example of free radicals addition reaction. Ethyl addition reaction. Most of the reaction of the alkenes are electrophilic addition reactions. Nucleophilic addition reaction. Aldehyde and ketones undergo nucleophilic addition reactions. Acetaldehyde, then it forms the acetaldehyde cyanohydrine. Known as elimination reaction. The reaction involves the loss of the atom or group of atoms of a molecule to form a compound and containing double or triple bonds. Thus, their reactions are essentially the reverse of the addition reaction. The common reaction of this type involves the elimination of atom or groups from adjacent carbon atom to yield carbenes. For example, propyl chloride plus KH alcoholic, then it forms the propylene. Elimination is further divided into two types as given below. Unimolecular elimination reaction. Even they are elimination reaction in which the ready remain in step involving one molecule. Only one molecule. For example, dihydrogenation of a tertiary alkyl halides usually proceed in even mechanism. Next one is bimolecular elimination. E2 reaction. Their elimination reaction is the rate of determination step involves the two molecules. For example, primary alkyl halides such as propyl chloride shown above generally undergo dihydrogenation by E2 mechanism. Depending upon the relative position of atom or groups eliminated, these reactions are also classified as alpha, beta and gamma elimination reaction. Alpha elimination reaction. The reaction in which loss of atom or group occurs from the same atom of a substance. For example, chloroform. After reaction, it forms the dichlorocarbenes. When is a beta elimination reaction is the reaction loss of one group or atoms occurring adjacent atom of a substance. For example, ethanol is converted in ethane in presence of concentrated H2SO form. That is the gamma elimination reaction. In these reactions, loss of the two atoms or groups occur from alpha and gamma position of a molecule, giving rise to the formation of a three-membered ring. 1,3-dibromopropane, then it forms the cyclopropane plus ZnBr2 in presence of Zn just. Rearrangement of reactions. These reactions involve either the migration of the functional group from one atom to the other, to the complete rearrangement of the chain of atoms present in the compound to form a new product. For example, primary bromobutane, then it in presence of 573 Kelvin AlCl3, then it forms 2-bromobutane. This rearrangement also takes place from the formation of electrophilic, nucleophilic, or the free radical intermediates. Interesting to note, a preparation of the first organic compound urea is synthesized in a laboratory involving a rearrangement reaction on ammonium cyanide. Then it gives heat, then it forms urea. Isomerization reaction. This reaction involves the conversion of one isomer into another. Then in molecular formula, carbon skeleton of a reactant always remains the same. For example, conversion of 2-butane into trans-2-butane to cis-2-butane is vice versa is a geometric isomerization reaction. Condensation reaction. There are the reaction in which two or more molecules of the same atom or reactants combine to form the product, which without the elimination of a simple molecule such as a water or alcohol. For example, when the acetaldehyde is treated with a dilute alkyl, two molecules of acetaldehyde combine to form 3-hydrobutanol. The reaction is also called aldol condensation. Molecular reaction. They are the reaction involve the reconjugation of covalent bonds either intramolecularly or intermolecularly through cyclic transition state under the influence of heat or light. These reactions do not require any catalyst and no ionic or free radical intermediate is involved. These are collectively called pericyclic reaction. Electrocyclic and cycloaddition reaction are typically example of such reactions. Electrophiliation. These reactions involve conversion of a cyclic diene and a cyclic alkenes and vice versa. For example, and cycloaddition reaction. These reactions involve addition of two unsaturated hydrogen atoms to form a cyclic product. Example of we will come across the detailed mechanism of reaction and take place to next. Energy changes during reactions. All chemical reactions involve the breaking and making of bonds. Since energy is required to break a bond, when energy is required released in the formation of bond, the occurrence of chemical reaction is always accompanied by the energy changes in one form to another. As we will therefore now present briefly and certain basic concepts regarding energy changes such as enthalpy of reaction, energy of activation, and the transition state. Heat or enthalpy of reaction. Heat or enthalpy of reaction del H is the total energy change with accompanies the conversion of a definite number of moles as required to the balance equation by the reactant into the product. It is possible to calculate the enthalpy of reaction on the basis of bond dissociation energy of various bonds broken and formed during the reaction. For instance, let us consider the following hypothetical reaction. Let us suppose that x1, x2 and x3 are represent the bond dissociation energy of the respective bonds involved in the reaction. During the reaction, two bonds A are broken while two bonds AC and BD are formed. Two bonds broken require a total number of energy while the two bonds formed liberate of a total of x3 plus x4 kilojoule per mole of energy. Therefore, the total energy change during the reaction, or in other words, rate of the reaction, should be x1 plus x2 minus x3 plus x4. It is dependent that energy assumed x1 and x2 is more than the energy required in x3 plus x4. Therefore, there would be overall consumption energy of the reaction should end endothermic and LH would be have a positive value. On the other hand, the energy consumed is less than the energy released, and the net elevation of the reaction would be exothermic and the LH should be as a negative value. Thus, the reaction between the methane and the chlorine. It is an isothermic reaction. It is result liberation of the 104 0.5 kilojoule of energy from very mole of the converted into methyl chloride. In the energy of activation theory, collision theory, an important feature of the most of the reaction where the endothermic or exothermic is the reaction required some extra energy of the reaction take place to understand the reason of. Let us recall the according to the collision theory of the reaction, the primary condition of the reaction is take place in that the reacting particles must come in contact to the collide with each other, but all the collisions do not result in the formation of product. In order to be effective in bringing about the reaction, the collision should fulfill two conditions. Then colliding particles must have the certain minimum amount of energy, such as threshold energy. The second is the colliding particles must be properly oriented with respect to each other at the time of collision. As far as the energy factor is concerned, most of the reactant molecules do not possess sufficient energy in their ground state for effective collision to take place. As a result, with such molecules collide with each other, no bond breaking or making take place, and the colliding particles bounce back or such. Therefore, the extra energy is needed to by the reactant to form the products. The minimum amount of additional energy required to the reactant to undergo effective collision is known as activation energy. E2 is the numerical equal to the difference between the threshold energy and the ground state of the reactant. That is, activation energy is equal to the E threshold minus E ground state. Most of the organic reactions have a activation energy in the range of 40 to 150 kJ per mole. If the activation energy has a low value, the reaction can take place at the room temperature. On the other hand, the reaction with the high activation energy take place only on heating. Energy barrier to the reaction. The concept of the activation energy means that the reactants have to be activated or raised to a high energy level before they form the product. In other words, there exists a certain energy barrier between the reactant and the product. In anticipating the progress of reaction, the barrier is generally represented as energy hump, which has to be surmounted before the reaction can be completed. It may be compared to a pass and a top of a hill separating two valleys. On the two sides of the hill, to move from one valley to the another, the one must move up to the hill and cross the pass. Similarly, the reactant must move up to the energy and level cross the energy hump to the yield of the product. Next one is the give free energy change. Gives free energy change. Del G is very useful pattern in the determining the flexibility and the direction of the concurrent dilation changes of entropy. Del H as is follows. When the oscillator is the standard state, the relationship may be written as the enthalpy term. Del H is directly related to the bond in the starting state and the products. A reaction takes place in the forward direction and is negatively charged. Del H is negative point lesser than that of reactions. On the positive value of the del G means the reaction has a tendency to take place in the backward direction. Del G is negative, his value is minus 2.303 RT log K. Transition state theory energy diagram of a reaction. The transition state there be useful in understanding the mechanism of organization and the energy changes take place during the reaction. According to them, reaction do not change directly the product, but the happens that have a reactant molecule come in contact with each other. It leads to the formation of a highly unstable arrangement of atoms whose energy correspond to the energy barrier separating the reactants and the products. The high energy species thus formed in known as activated state or the transition state. For example, single step reaction represent as A plus B minus C is after reaction A minus B plus C. The high energy transition state may represent at the dotted line indicate the partial bonds. The transition state nearly represents a probable arrangement of the atoms correspond to the atom in barrier to the bond partially but not completely broken in the two new bonds and begin to then is not completely formed. It is not representing substance which can be isolated or even reacted. As soon as the transition state is formed, it is split into the product. Thus, the completion sequence may be represented as reactants that form transition state and form the products. The free energy difference between the reactant and the transition is known as the free energy activation, denoted as del G. Psi determines the rate of the in which reactants such as transition state in which determine the rate of reaction. A small value of del G means that there is only a small difference in energy between the reactant and transition state, and therefore the reaction takes place press rapidly. Conversely, a large number of del G means the reaction takes place slowly. Transition state is between which reactant and concentration is determined the equilibrium constant K. It is relatively free energy of activation. Del G is equal to del H minus T. Del T del S is equal to minus 2.303 RT log K. Del is enthalpy of activation and the del S is in entropy of activation. Note the super sub Note the subscript known as double integer is always used that referring to activation parameter involving the transition state. Figure 2.3 shows the free energy of reactant transition state and products free energy involving the formation of transition state in the net force charge is for a single step, such as diagram shows the energy of the various species and the energy changes take place during the progress of a reaction belonging to the end of the energy profile of a energy diagram of the reaction. It noted that the Z depending upon the values of del G and del G. Energy diagram for multiple reactions. The reaction may be proceed on the reactant or product either directly in the single step known as the concerted reaction, or it takes place through a two or more step formation of the more intermediates. Such reaction is directly converted in the products without the formation of intermediates. It is converted in reaction then of having only two energy minima correspond to the reactant and the product, and the maximum energy correspond to the transition state in figure in 3.2. Most of the reactant organic reaction compounds are multiple step involving the formation of the one or two more reactive intermediate. Let us consider the complete reaction that form transition state then form the reaction intermediate. Reactive intermediate then form the transition state, then it form the product. In such reaction, we draw an energy diagram in each of the individual step, and then it is joined together in the middle of state acts as starting material for the step 2. Since the intermediate has a high energy and then the reactant and the product is reactive and may be isolated. However, unlike the transition state, depending intermediate has a miserable lifetime, and depending upon the energy barrier activation to instead the free energy diagram can be two types and so on. First is if the energy in free energy activation transition state is more than the transition state, and the energy diagram is shown in figure 3.3. In such cases, the intermediate is converted in the product and can be seldom isolated. The first type of the reaction is the rate dimension of reaction. Second is if the free of the reaction of the transition state 2 is more than the transition state 1. The energy diagram is shown is 3.4. In such a case, intermediate rather than the second step of the reaction consider the rate determinant of the store reaction. 3.5 figure shows the energy diagram of the isothermic reaction in terms of E for E reaction. 3.6 shows the diagram of the isothermic reaction. You noted that these diagrams are difference in the energy towards between the reactant and the transition state to be present. The activation, the difference in energy levels between the reactant and the product depends on del H. For the endothermic reactions, E activation must be at least as large as del H, although generally it is larger. For the exothermic reaction, E activation may be higher or low. Generally, it is on the lower side. Development of structure and transition state hormone postulate. In order to fully understand reaction, it is necessary to completely understand the structure and energy of the transition state, which leads to the formation of product. But the transition has only a transitionary existence, shown as the form during the course of a reaction. It changes into a more stable species, but it is possible to idea of the structure a particular transition section diagram with the hormone postulate. Hormone 1955 advanced a generation known as hormone postulate to convert the constitution and transition according to the postulate structure of a transition state most clearly resemble to the structure of the stable species that lies closest to its energy. For example, a strongly exothermic reaction as the energy level of the transition state is must. For example, in strongly exothermic reaction, level of the transition state is such clear to that the product of the reaction. Therefore, the transition state should be accepted to closely resemble to the product and structure as well. On the other hand, the strongly exothermic reaction, the transition state is generally much closer to the reactant than the product, and this result in the strong resemblance to the reactant structurally. For a For a two-step reaction, the first transit state may structure resemble either the original reactant or the intermediate, whichever is closer to its another. The second transit state is may resemble structurally even to the intermediate and the final product according to which the energetically closer to it. Effect of catalyst to the transit state. The many reactions which we study involve in the use of stable carbon and increase the rate of reaction with the state and the search of the reaction for an alternate path for the reaction required for the that direction energy. It may be pointed out, however, that the energy and the reaction remains unchanged even in the presence of catalyst. Assigning from one charge is intermediate and another unspecified understand studying the various reaction intermediate may be found that the species may either carry positive or negative charges or they may be neutral in character in order to product whether a given species carries some charge or not. We not present a very simple method knows a formal charge method for the charge expansion or intermediates. Formal charge is amount of positive or negative charge when they are assigned to a atom or a species in order to how the now whether the species of a whole carries some changes or not. The calculation of the formal charge is the comparison of the atom sector in neutral to the few free state and the number of the valence electrons associated with the atom in a bounded state. The difference between the two values given the formal charge in the atom of any given species. Formal charge on an atom is given species number of the valence electron in the free atom minus the number of valence electron in the bounded atoms. Calculation of the number of bonding to calculate the number of electrons associated with them. Then the number of bonding electrons then this form the last carbon ion was known as the carbon and negative charge species in which the carbon atom negative charge is rationalized. This may be considered the structure of the carbon ion.